Chapter 10, we're going to take a look at heat energy, internal energy, temperature, and related types of topics. We're going to define temperature as the average kinetic energy of substance particles. There are three types of kinetic energy, three types of way particles can move, whether they're in a solid, a liquid, or a gas. There's translational kinetic energy, there's rotational, and there's vibrational kinetic energy. When we talk about things that are hot and cold, what we're talking about is relative amounts of heat or internal energy that one substance has compared to another substance, and primarily compared to our skin temperature. When we add or remove energy, many times, but not always, what we'll encounter is a temperature change of our substance. When we have higher temperatures, we have higher average kinetic energy of our particles, and what those particles do when they collide is they collide more vigorously, and when they collide, they push away from each other more rapidly. They collide with the walls of the container more vigorously, so if we're talking about a gas, it will cause an increase in pressure. When we're talking about solids or liquids, because they're colliding and pushing off of each other, and they're pushing off of each other with more energy, what that causes the substances to do is increase in volume. So that is described as a coefficient of volume expansion, and that is a property that is specific to each substance. In general, solids expand when they become liquids. However, water is the exception. And think about this time of year, liquid water is actually more compact, has a smaller volume than solid water or ice. H2O expands when it freezes. That's why when you put liquid in the freezer, it tends to disrupt or rupture the container. And if I take the same mass of H2O as a liquid and I put it in the freezer, volume increases, mass doesn't. The density of ice is lower than the density of water. How do we measure heat flow? We measure heat flow using a thermometer and looking at temperature. There are a number of temperature scales that are listed: Fahrenheit, Celsius, Kelvin. In science, we use Celsius in this unit, and when we talk about gases, you use Kelvin. The reason for Kelvin, it is all positive temperatures. Absolute zero is the lowest. Anytime we're working with gases and we're multiplying by temperature, we want to make sure that none of our quantities become negative, because we can't have negative volume, we can't have negative pressure, so our temperatures all need to have positive values. So Kelvin is the one that we will be using again in this unit. 0 degrees Celsius, remember, is equal to 273 Kelvin. And when you write temperature in Kelvin, remember there's no degree sign. Internal energy of something is the amount of energy it has due to its particle motion. And when we talked about dissipated energy in earlier units, generally what we're referring to is the substance's internal energy. When I have kinetic energy that dissipates, or gravitational potential energy that dissipates or seems to disappear, where it generally goes is into the substance to increase the substance's internal energy. We said that internal energy was the energy of the substance due to particle motion. It can also be due in part to the potential energy of the particles, but since their relative position to each other is so small, not measurable with the tools that we have, we're going to focus on internal energy approximating the kinetic energy of the particles. And since kinetic energy depends on or is related to the temperature of a substance, primarily a gas, we're going to focus mostly on gases. There is an equation, we're not going to derive it because it takes too long, that has kinetic energy of a substance equal to 3/2 times nRT. N is the number of moles, remember. R is the universal gas constant, and in this case we're going to use 8.31 joules per mole Kelvin. And T is temperature, and the temperature we're going to use is in Kelvin. So if we know the temperature of a substance, we can figure out the average kinetic energy of the particles. If we know how many moles we have, we can find total average kinetic energy of the substance. If we know the change in kinetic energy, that is equivalent to the change in internal energy, and that is equal to 3/2 nR times the change in temperature. A couple of vocabulary terms we'll make sure that everybody's clear on. We all have the same definition. We're defining heat as the energy transfer between two substances due to a temperature difference. Heat energy is going to flow to something that is cool from something that is warm. If we have two things that started out with different amounts of heat energy and we put them in contact and we leave them in contact long enough, what we notice is they eventually arrive at the same temperature. When that happens, we have the condition called thermal equilibrium. So in order to have the thermal equilibrium, we need to have those two substances in contact with each other, and so they will eventually reach the same temperature because heat is flowing from the warmer substance to the cooler substance. We defined energy transfer as work. We can also have energy transfer by heat. When you rub your hands together, your hands have kinetic energy because they're moving, and if you rub them long enough and fast enough together, you'll notice that your hands warm up. So the rubbing of the hands is kinetic energy. The hands warm up. So what that does is that increases your internal energy of the particles in your skin. Internal energy increases, which means that the temperature increases. So we can do work to cause the temperature to change. We can add heat or remove heat. Remember that work we defined as a change in energy. And it can be a variety of different kinds of energy that we change. Specific heat. This is a quantity that you dealt with when you were in chemistry. We will review it a little bit here. Specific heat is the amount of energy that you need to raise. This time we're using kilograms instead of grams. Raising 1 kilogram of a substance by 1 degree Celsius, could be or Kelvin. Symbol for heat, specific heat is, in this course we're going to use capital C for capacity, and we're actually going to have two of them. We'll have C sub P, which is the heat capacity at constant pressure. This is the one that you used in chemistry. At constant pressure means you have an open container. The pressure in your system is equal to the pressure of the surroundings. So there's no change in pressure. There's also a heat capacity based on constant volume. You use it in the same way. The difference is you would have now a sealed container, and whatever process is going on in your sealed container, the pressure may change, but the volume is constant because you have a rigid container. We use a calorimeter in general in a chemistry lab to figure out the amount of heat, and Q is our symbol for heat. If we take a look at a specific heat problem, physics-based this time, we have 0.05 kilograms of an ideal gas, and we heat it to 100 degrees Celsius, and we started at 42 degrees Celsius. We want to find out how much heat the gas gains by warming it up. The specific heat of the gas, 650 joules per kilogram Kelvin. So the equation that we use, specific heat equation, is Q of the substance equals its mass times its specific heat, either pressure or volume, times the temperature change. So the mass of our gas is 0.05 kilograms. Specific heat of this gas is 650 joules per kilogram times degree Kelvin, and our temperature change. Temperature change, final temperature is 100, but we have to do this in Kelvin. So 100 degrees is 373 degrees in Kelvin. 42 degrees is 315 degrees in Kelvin. So there's our temperature change, and we do the math and we get 1885 joules. Now we added heat. This number is positive, so Q is positive when heat is added. So if Q is positive when heat is added, that must mean that Q is negative when heat is removed. Heat of fusion, heat of vaporization. Fusion is the term that's used when we're talking about heat flow for something that is either freezing or melting. In other words, it's the phase change between solid and liquid. And if you think about what goes on with a substance when it goes through a phase change, its temperature remains constant. All the energy, heat energy, going into a substance or leaving a substance during a phase change is associated with the particles coming together and either overcoming the attractive forces if I'm melting, or allowing the particles to get close enough for those attractive forces to form if I'm freezing something. So heat of fusion is the heat involved in a phase change between solid and liquid. Heat of vaporization, so we're looking at boiling, or when I go from gas to liquid or condensing. And again, for heat of vaporization, it's the heat involved in a phase change between a liquid and a gas. Both these terms, heat of fusion, heat of vaporization, are referred to as latent heats, stored heats. And the way that I would figure out the total amount of heat energy involved is I'm going to take either the mass or the moles and multiply it by the value of the heat of vaporization, heat of fusion. Whether I use mass or moles depends on the units of the heat of vaporization, heat of fusion. And that would be information that would be provided when I'm trying to do a problem. So what happens to something when you heat it enough and it starts boiling? What happens to its temperature? While it's boiling, the temperature remains constant. You put a pot of water on the stove, turn it on, the water warms up, eventually starts to boil. If you turn the heat up higher, bigger flame, hotter burner, it won't boil at a hotter temperature. It will simply boil more vigorously. More of the particles in the liquid will get enough energy so they can go from liquid to gas. But the temperature doesn't change until all that liquid has become gas. Talked about heat as a transfer of energy. If something transfers energy easily, it is called a thermoconductor. In general, what kinds of things would make good thermal conductors? Something that transfers heat easily or quickly. General metals are your best thermal conductors. Thermal insulators, then, on the other hand, would be things that don't allow heat to be transferred easily. That's why cooking utensils used to be, and still in some cases are, made of metal. You put something metal on a burner, it will transfer the heat to whatever you're cooking quickly and easily. If you want to keep something hot, you don't want to put it in a metal container because the heat will go from the substance to the container very easily, from the container to the surroundings, usually the air, pretty easily. So you put it into something that's a poor heat transfer material or a thermal insulator. Non-metals, if I'm talking about elements. Gases. Gases are really good for thermal insulators. Air is a really good thermal insulator, which is why in the winter you layer on clothing. Cloth, thermal insulator, because it's not a metal, will not transfer your body heat out away from your body very easily. And between each layer of cloth that you put on, you've got a very thin layer of air. Air is even poorer thermal conductor, better thermal insulator than the cloth. And so you have multiple layers of air, you've got multiple layers keeping that heat from leaving your body. When heat is flowing, when energy is being transferred, there are 3 different ways that heat energy can be transferred from one substance to another. First way to transfer heat energy is called conduction. For energy to be transferred through conduction, the 2 substances must be in contact with each other. The second way that heat can be transferred is by convection. For convection to occur, what happens is we have a fluid required, and the cold fluid is warmed and moves to the substance to be warmed, surrounds it, and warms the substance. So it's a 2-step process. A convection oven works in that air is your fluid. So the burner warms the air moves around the substance and warms the substance. The third way that heat is transferred is via radiation. And radiation is the transfer of electromagnetic radiation. So if I want to talk about infrared radiation, then I can talk about the infrared energy traveling from the source to whatever I'm heating. But radiation, again, sticks primarily with electromagnetic radiation, convection, and conduction. You can think about in more conventional terms, a burner, an oven. That takes us through Chapter 10. Next we look at Chapter 11 and thermodynamics.